matrix. Observe here, any plane is there, its normal vectors equation is 1, 2, minus 3, minus 1. This plane is the null space of what matrix? For this matrix, it is the null space. For this matrix, it is the null space. So this question is over. Next we will go to next number. Describe the subspace of RQ. Is it a line or plane spanned by these vectors? So here two vectors. Observe this is this into minus 1 is this one. Hence they are linearly dependent. Hence only one, these two vectors span is same as one vector span. So one vector span is a straight line passing through origin and this vector. Okay, next is three vectors 0, 1, 1, 0, 1, 1, 1, 1, 0 and origin vector. Origin it is of no use, it is always linearly dependent. Then these are two linearly independent vectors. Two vectors with origin always span a plane. So it is a plane in the RQ, and what that plane is? Y is equal to 1. It is a plane. No, y is equal to 1. It's a plane passing through origin. So how y is equal to 1? So it is a plane passing through origin and these two vectors. Next is the columns of a 3 by 5 echelon matrix with 2 pivots. As 2 pivots are there means number of vectors, linearly independent vectors are 2. So 2 linearly independent vectors 3 by 5. So how many vectors are there in, how many components are there in a column? It is 3. So what it will give me? It will be giving me a plane in RQ. Next, all vectors with positive components. It is whole RQ. There are several vectors with all components positive, which are linearly independent vectors. But so out of which any three vectors of it will form a basis for RQ. Hence they span the whole RQ. So this will be whole RQ. It is written only whatever we have discussed now, it is written here. Here it is whole RQ. Here it is a plane in RQ. It's a plane passing through these two vectors and origin. Next question is, find a basis for this. Here x and y, x is pivot, y and z are free. We have to allocate likewise. Here this is the equation, y and z are free. I have substituted 1 for y, 0 for z, again 0 for y, 1 for z. We obtain the corresponding values x. In the first case we are getting 2. This is my x. Here I substituted 1, here 0, that means x is equal to 2. Similarly here 0, here 1, I am getting x equal to minus 3. So these are three vectors I am getting. So these two vectors form a basis for B. So here this is, let this vector be E1, let this vector be E2. Find a basis for the plane with xy plane. Find a basis for the intersection of that plane with xy plane. I have a plane, this plane, and it is having intersection with xy plane. That means its z components are 0. Once for this matrix, it's for the intersection of the given plane with xy plane, its z component will be 0. So z component is 0 means in the equation it is x minus 2y plus z. So this component is 0, y is free and x value is 2. So only one vector, we will get only one free variable. So one vector, that one vector is 2, 1, 0. So hence the basis of intersection of the given plane with the xy plane is this span of 2, 1, 0. Next question is set of all vectors perpendicular to the, find a basis for all the vectors perpendicular to the plane. Now always we know in the plane the normal vector is 1 minus 2 plus 3. 1 minus 2 plus 3. Now let us verify it. So its name is E1, its name is E2. Now what we are getting? My vector 1 minus 2, 3. We will do dot product. So this is my 1, this is my V vector. Okay. So here V transpose E1 is how much? It is the K. Please observe 1 into 2. It is what? 2 into 1 V diagonal, V diverge. So it is 1 into 2, then minus 2, then 0. So it is 0. Similarly, minus 3 plus 0 plus 3, it is 0. So the dot products are with E1 and E2, it is giving 0. Hence, as it is every basis vector is orthogonal to V, hence V is orthogonal to the whole space. So what is this V? 1 minus 2, 3. This vector is orthogonal to the whole space. So basis is it. This is the basis of all the vectors which are perpendicular to the plane. And next question is, which of the following are bases for R cube? Because here two vectors cannot span R cube, so they will not form a basis. Four vectors are not linearly independent, so here span is not equal to R cube, hence they will not form a basis. It will not form a basis because they are not linearly independent. Now these vectors are linearly independent because the corresponding matrix I wrote 1, 2, 2, minus 1, 2, 1 and 0, 8, 0. This matrix, what operation I will do? So here R2 plus R1 stored in R2. What we are getting? We are getting so R2. So first row and second row it is 0. First row plus second row it is 4. 2 plus 1 it is 3. So this is. And third row as it is kept. Now I have to make this element 0. So I have to do the operation R3 minus 2 R1 stored in R3. So first two rows remains as it is. Third row is 0 minus 0 is 0. 8 minus 8 it is 0. Then 0 minus 6 it is minus 6. So last row is minus 6. So there are 3 pivots. That means rank is equal to 3. That means number of vectors is equal to rank. Hence the vectors are linearly independent. Any 3 linearly independent vectors of R cube always span R cube. Hence it will form a basis. So yes, the vectors form a basis of R cube as any three linearly independent vectors of R cube form a basis for R cube. Now the last fourth bit, it is everything remains same, but the last 0 is replaced by 6. So here the first operation as it is remaining same, and here next I will get the echelon form, and in the echelon form I will get two pivots because this minus this minus 8, this minus 6. So it is 0. So as one of the pivot is missing, rank is equal to 2, which is less than the number of vectors. Hence the vectors are linearly dependent, and any linearly dependent vectors cannot form basis. Hence they cannot form a basis for R cube. Hope it is understood to the viewers. So with this we will conclude this video. In next video we will do few more problems. Thank you for your patient listening.